So hello, welcome to this session. The name of the session is So You Want to Be a Machine Learning Engineer? My name is Antons Mislēvičs, and I'm leading a team of data scientists and machine learning engineers in CTCo. So this is what we do day to day. And you've heard some facts about me already. I've spent over 15 years in IT already. Maybe, yeah, even a few more years. This slide maybe is outdated. 10 of these years were at Microsoft Consulting as a technical consultant. Those of you who worked with SharePoint perhaps have met me. Maybe you're still using some code, what I've written, because I was working closely with SharePoint engineering teams for the last 3 of these years. Very fun experience, a lot of international experience, a lot of flying around and working in different countries. In parallel, I finished my PhD thesis. And as everyone who has PhD, we're still related to universities where we've done it. At least I think that this is like normal practice in Latvia, at least. And yeah, I'm still associated with Riga Technical University as well. With this slide deck, actually, when I was invited to speak about machine learning here, first I was thinking this will be DevClub number 100. So I was thinking that this is why they invite me. But now I realize that because I am invited, this is not 100, right? So they want to have 100 when Antons will not be speaking. So yeah, that was interesting. But yeah, I was thinking like, okay, what do we talk about? Because over this last maybe even 5 years already, I was doing a lot of presentations about machine learning because we tried to make machine learning more popular. We tried to describe people what machine learning is, how it works, encourage them to start training some models, play with machine learning. And that was actually good because we had a lot of sessions for different audiences, for developers, for business stakeholders, for architects, different topics as image recognition, natural language processing, just an overview of machine learning for example, predictive maintenance was one of these. And also I had organized few, or not I have organized, I was invited to speak in few closed events with some companies in Latvia, and not only in Latvia. What they wanted was to educate the management staff, the decision makers on what machine learning is and how it works. And I think I'm not the only one who was doing it, obviously. And because of all this, and because machine learning had become so, let's say, not affordable, but so easy to start doing it, and people started like thinking about it, we see more and more machine learning projects, right? On the other hand, because of this growing popularity, I think machine learning starts getting some incorrect attitude to it. And many good engineers are not going to machine learning because they think that, some of them think that machine learning is something like what you see on these cartoons, what I just picked this morning in the internet, like machine learning system like this one, like what you see like on this one is just like, this is your machine learning system, right? You just throw in some data and then it just does something. And if it does something wrong, you just tweak some things, like steer the pile until they start looking right. Some of people think that data science work is something like what you see here. So it's like data scientists are not doing much, and it's like when they don't do something, they're having fun, and then it's like, what do you do? We're training model forever, and while doing it, we don't do anything. And this last one, I also liked it quite a lot. It's like this one, right? So it's like, our brain is complex, deep learning networks are complex, so deep learning works the same way as our brain. And obviously, this doesn't make good reputation for machine learning, and I can understand why many engineers do not want to associate their future with machine learning, because some of them think that machine learning, it's not serious. It's like playing with something and the machine will learn that. Where is engineering? It's not real. It's not proper engineering. Others are having completely different opinion, like machine learning, oh, you must be very strong in math to do machine learning. If you are even an engineer, you need to understand data science, you need to understand math. And this is why we cannot go there, because we don't have that foundation. And both of these views are wrong. And I truly believe that if you are a good engineer, you can have really great, very interesting career in machine learning engineering. You just need to know how to start it, and you just need to understand what engineering in machine learning means. And that's why for this presentation, I wanted to structure it this way, sorry. I'll start with speaking about some cool machine learning projects, what maybe a lot of us hear about, and give you my perspective on this, why these projects are not so cool as maybe they first sound. Then I want to talk a little bit about enterprise machine learning projects, or something what we do, because we as CTCo work for very large companies, international companies, and we deliver to them machine learning projects. And I call them enterprise just because I haven't found better word for it. But basically, yeah, this will be the second part. And finally, I'll touch a little bit on how you can use this, what you've learned today, to become a better machine learning engineer. Usually at this point, I ask, does this agenda sound good to you? I don't hear you. Perhaps you're crying like, yeah, move on, it's great. And so now I'm moving on. Let's start with a cool machine learning project. Usually, what is a cool machine learning project? It's any project you hear about, and we hear about a lot of these projects when we go to some events where people share something about projects, what they've done, some startups, for example, someone who's new to machine learning, they're very excited about machine learning. So what are the prerequisites? They have a client excited about AI. So the client says, I know AI can do a lot of things. I want to have AI. Then client has some data, preferably a lot of data or some interesting data. And then we have someone who is called machine learning engineer or data scientist. There is like, some people tend to call themselves as we are scientists. Others are saying, no, we're engineers and we do machine learning. But it doesn't matter. Basically, this is someone who is excited to try some modern deep learning algorithms, right? And preferably this person who wants to try, this person has some knowledge of Python and they have access to some compute resources, some gaming desktop or gaming laptop with a video card, or maybe some virtual machine in the cloud with GPU. So it's Azure, AWS, Google, whichever cloud. And this is a good prerequisite. Then this person knows something about what machine learning can do, and their client perhaps also knows something about what machine learning can do. For example, machine learning can take some input images and solve classification tasks. So you are training the model, it will be pretty deep, for example, convolutional neural network, as you can see here. This one specifically is not very deep, but you may train much deeper one. And then basically what this model will do, you feed in your image and it will give you probabilities. Is it a cat or dog or some other animal? And then having this in mind, the client can say, okay, this problem looks very similar to what I want, but I want to classify cats versus dogs. What machine learning engineer or data scientist will do? They'll go to their favorite search engine. I've removed logo here, so you can use any search engine for this. It will work perfectly fine. You just put like cats versus dogs, deep learning, you get a lot of results, how you can solve it. You get a code, and then from this code, you can train something, and you're spending, this engineer or scientist is spending a lot of time trying to massage clients' data so this code works. And basically, this is where a lot of people say, this is where invested a lot of work. We figured out how this complex model could work on our data. We trained it, and then we received this. So it's like, sorry, this one is lagging a little bit, but I'll get used to it during the presentation. So it's like, this is our training set, this is our test set, and this is our accuracy. Accuracy, 97.6%, great accuracy. And the client is saying, let's go into prod. And then what this machine learning engineer or data scientist is doing, you go again to your favorite search engine, you say like, for example, in Python, machine learning model, how you can deploy it as a web service, and you get a lot of links, you pick some of them, you implement it, boom, it's in production. Client is happy, you are happy, you are very proud, you go to conferences, you talk about it. Not on a stage, but just to other people. And then when we hear stories like this, we start asking questions. And questions what we have, since we're working on this field, are, for example, the following, like how do you split your data to train and test? What are some sources of bias in your data? What was your baseline model? How you were improving it? How you were measuring how you're progressing during improvements, how you're tracking this, and all that. You see, long list of questions. And when we go into this discussion, usually these people become less enthusiastic, and they're like, yeah, but why are you asking? We have 97% accuracy, 97.6 even. It's great accuracy. Just leave us alone. Why are you asking all this? And it's not because we just want to somehow make them feel bad or something. We're really interested in all this. And in our projects, actually, we spend a lot of time working on all this. And why we're asking this? Because basically modern machine learning models, and I'm mentioning it many times in different presentations, that they're black boxes, right? You have some input, you put it in the black box produces an output. And if you don't ask questions, if you don't try to look at this black box, this is what will happen. It will just bite you at some moment, and it will bite you, and it's fine because it's kind of your responsibility, but it will also bite your client who maybe is not guilty. They just wanted some cool machine learning model, and they should not know how it works from the inside. With this, I want to switch to enterprise machine learning project. And enterprise machine learning project, as I mentioned, this is something what we do for our clients. I'm not saying that this is the right way to do machine learning. This is how we do it. So when you look at it, be skeptical, challenge what you see. If you see that something will not work for you, that's fine. It works for us. If you haven't tried something, try it, maybe it will work for you as well. When I was preparing this presentation, I was thinking like, okay, after this slide about enterprise machine learning, maybe those of you who are familiar with machine learning and machine learning operations, ML ops concepts, for example, we will immediately think, okay, Antons will now spend remaining half an hour talking about these diagrams, like what ML ops is and how this crisp MLQ cycle works and all that. No, I will not. I've put links here as always on my slides. You see these links here in the bottom of the slide, so you can go and check them and read about it by yourself. I will not speak about it, not because I don't trust that this is right. This is right. But this is more to me like some nirvana state where you want to be. How you get there is very different because you may use different technical stack in your project. You may have different baseline where you start from. And that's why instead of this, I really encourage you to go and read through this if you are really interested and you see your career here in machine learning engineering. But I'll be using slightly simplified model, which works for us, where we have basically 5 blocks, project organizational management going through entire project. And then we have research to engineering, production operations. And here under this chart, you can see this line where basically what you see is how the amount of work done by data scientists and machine learning engineers changes. So data scientists do a lot of work in the beginning and less work as we go to production operations, and machine learning engineers other way around. They do some work during the research, but they do more work when we go into production operations. And now what I want to do, I'll go through these 5 blocks and about each of them, I'll share some tips, maybe some learnings, how we approach it. And about each of them, I want to share some goals of these blocks and then some practicalities, how we practically solve it. When I was preparing for this presentation, it was really hard to balance between going too deep into some of these topics, because actually each of these 5 blocks can be a half-an-hour presentation on its own. And we can do a follow-up on any of these 5. So if you see that you would want to learn more about some of them, I will be happy to share how we approach it and do more. I don't share maybe more today just because we don't have enough time. Let's start with the first block, so project organization and management. And this is very important because I believe this affects all of the remaining stages. This affects your relationship with the client, and this affects how professionally you do machine learning at the end. So how do we see it? For us, goals of this phase are the following. First, we want that data scientists are focusing on business goals and outcomes. So throughout the project, when data scientists are doing research, they don't want to apply latest, greatest algorithms from newest scientific papers, because this is just great and they're scientists and they want to do science, but they focus on business goals and outcomes. Then we want client to understand and accept the risk of going into the research, because machine learning project, it's not entirely, for example, software development project. There is some risk, and you want your client to know that it is not yet guaranteed that you will succeed in the end of the project. And finally, we want to be transparent. So we want our client to, if they come to us and ask, where have you spent our money last year? We can show them. We can show them what we were researching, what are the outcomes, what we've learned, what we've maybe abandoned at some stage, and why we've done it. In order to achieve it, this is at a high level of the process, what we are following. We start with ideation, where we talk with the client, we try to understand what do they want to solve with machine learning? What are their real business problems? And then we try to understand if these business problems can be solved with machine learning or not. Then when we've understood how machine learning can be applied, we go into the research. If research was successful, we go into the pilot implementation to try it out with the real users and see if these models actually make sense for business. And if we're good with the pilot, then we go into full implementation. And usually this is where the full implementation team gets involved. If we look specifically at the research stage, we do it in iterations, where we have a list of business scenarios from the user, from the client, sorry. We split it into a list of hypotheses, and then we start picking these hypotheses one by one and do a research iteration on them. It can be a technical POC, it can be a research, and each hypothesis is something what we need to validate in order to get one step closer to the final solution. One iteration lasts around 2 to 3 weeks. This is how we try to keep it. At the end of the iteration, we prepare results presentation for the client. And then if the client is happy, we may go into the pilot. If the client is not entirely happy, let's put it this way, and this is where we end up very often, we come up with a new list of hypotheses and we just throw them in the backlog, and then we pick them from there and continue. And if the client, we see that something cannot be done completely, for example, we don't have enough data, or our model is not performing completely, we don't have ideas how to improve it at this point, then we can just decide to abandon something, and we stop there, and then we record that, yeah, we decided to stop there, and these are the reasons why. Now, when it comes to ideation, it's not like we come to the client and say, you know, what do you want to do? Let us help you with machine learning. We can do whatever you want. What do you want us? Because usually such discussions doesn't lead anywhere. So we try to come prepared. And this is an example of how we come prepared if we know that the client is interested in something related to document processing. We know that document processing from a business perspective is 3 stages: is ingest, process, archive. And at each of these stages, it doesn't matter with which documents you work. First, you ingest them. For example, you do OCRing, you extract some metadata, then subject matter experts are processing them. And then when decision was made, document was processed, you put it in an archive. And depending on the stage, there might be different machine learning models that work on each of these stages. Like, for example, in ingest, you may want to detect language automatically, or detect OCR quality, or do some basic classification to understand, is it the document you're looking for or not. In processing, you may want to do something more business added value, let's put it this way. Like, for example, you want to summarize the document. And in archive, you may want, for example, to select documents for detailed audit. So we show this map and we tell to the client that basically your final machine learning solution will not be one of these, but it will be a combination of this. So it may be detect language and classification, and then summarization of documents, and then something else. And then we can open, this is an example for ingest phase, we can open this stage up, we can describe these models in more details, and we can put this complexity score or risk, this, for example, low, on each of the models. And this lets our client know what is the risk going into research with this model. Like, for some models, it's low. For example, visual document analysis, it's already medium. For something else, like document summarization, it will be even high. And then the client can understand, considering the budget, what they have for the year, how they want to play with it and what they want to do. How we do it practically? First, we use team data science process. We don't use it entirely. We've adjusted it slightly. There is a link to TDSP. You can go and read. I highly encourage you to do so. Then we use Azure DevOps to track these things for each research iteration. Like, here is an example, and you can see we have idea, hypothesis, user story. And then after it, we have Jupyter Notebook with which we are connecting to this Azure DevOps environment. And we are generating the report like this. So this report, what you see is basically where we generate it automatically, and it's like, you may think of it as a research log where we put some metadata on tasks in DevOps, like, for example, hypothesis result. When it is closed, by filling in the result. And then the Jupyter Notebook can generate nice looking research log with all the results, what we can then show to the client and say, this is what we've done, this were the results, this is why we've closed. So we don't need to browse through the Azure DevOps for this. Now, let's go to the second stage, which is research. Here, for the research, our goal is that data scientists understand data and business tasks. And this is what is machine learning. It's not about massaging data to make it work with specific complex model. It's about understanding data, understanding business tasks, and learning how to translate from specific language of this business to data, to science, and back. Because business doesn't know what classification is, what clusterization is, what regression is. Actually, they do not care if you will be using convolutional neural network or some other type of neural network. And this is the task of data scientists, how we see it. Data scientists must work with data, and they must work with business. Then when we've trained the model, we want to be sure that the model is correct, stable, and fair. And we are very skeptical about it. It's like, if we're getting 97.6% accuracy, it's like, but why? But is it for everyone? Is it only for male or female? Is it for all gender categories? Will it change over time or not? And we try to investigate it, because this is what we want to show to our clients. And again, this is data science. Data science is not about massaging the data to make it work with your model. It's about learning more about your data and learning more about your business. And finally, we want to achieve that our client understands what results have been achieved by the model and what are some limitations of this model, because they will need to make business decisions based on what we're giving to them. What we do practically. First, we focus a lot on train test split. So if you are saying we did just random split, okay, we did stratified split, so everything is fine. We did stratified split, right? This doesn't work. Here is an example how we do it for example, in one of our projects for medical data set, we had data about patients. So we make sure that every patient, we have multiple, for example, images for one patient, medical images. Every patient will be in one set only. Then we know that there are some critical attributes that can affect the disease we're looking for. Not because we're so smart, we asked medical doctors and we've read some medical literature, and this is where we picked this out. So we've read some articles and we validated it with doctors, and then this is what we wanted to balance. And then we try to keep pretty large test set. And here you can actually see that different attributes, the proportion between train and test is approximately the same. It's like 1 to 2 approximately for all of them. Then it's good practice to start with some simple baseline model and then gradually improve it over time. If you do a lot of experiments and you want to compare these experiments, there are tools to do it. We use MLflow. You can use something else. We don't. We are also guilty. We don't do it in all of our projects yet, but this is where we want to be. And in the projects where we used MLflow, actually, we're quite happy with that. And then it is always a good idea to validate if the model what you've trained, if it is fair and if it is non-discriminating. Maybe it's a hard topic. We can pick this one for half an hour, because obviously all classification models are discriminating by design, but at least you need to check common things like gender, race, age, something else what is important for your specific model where you train it on. Just be critical, think about it, because this is what data science is. Again, it's not about massaging the data. Now, the next step, what we do also is developing a business strategy. And this could be a good way to explain how the model will affect the business. I think some of you may be familiar with the confusion matrices, and I'll spend some time explaining this. So it's basically what you have. Here is a confusion matrix for elevator door repair prediction. So it is the model tries to predict if the door will stop working or not, right? And this one is actual value. So this is when the actual value was, for example, defect. This is when the actual value was healthy. And then in columns, we have predicted values like defect and healthy. And what you need to know is that model does not tell you if there will be a defect or healthy state of the door. So the model will give you probability from 0 to 1. And for example, 1 means that there will be a defect, and 0 means that the door will be healthy. And it's up to you how you work with it. For example, what you can do, you can say, okay, model, if the probability what you return to me is 0.2, I want to treat it as a defect. Or you can say, okay, if the probability you return to me is 0.99, I still want to keep it as healthy because I want to have it as a defect only when you are really sure about it. And this really depends on your business case. Like, for example, if you are training a model to find doping or something like that, you want to keep it really strict. Like if the model is 99.9% confident, only then you like bring it up and you start saying that someone has a doping, because it's pretty strict case, let's put it this way. And then basically adjusting this cutoff point, you can affect how frequently the model is ending up in each of these squares, and you can apply cost to it. Like, for example, the model had predicted that there will be a defect, and there was a defect. You went on site, you did proactively some maintenance, and you paid €200 for this. The model predicted that there will be a defect, but the stage was healthy. You went on site, you still did maintenance, so you paid €200, but actually you were able not to pay it, but you paid it, right? So it's still a cost for you. Now, the model said everything is good, everything will be healthy, but there was a defect. You haven't done anything, the door broke, you went on site, you needed to repair it urgently, and this is why you spent €600, for example. And the last state is where the model said it is healthy. Oops, it's hard for me. It's actually lagging quite a bit. It is healthy, and it was healthy. You were not doing anything, and you saved some money, right? And this is where adjusting cutoff point, you can play how frequently you end up in each of these squares, and you can discuss with your business, like, what is your business strategy? Where do you want to be? Or how much money we will save with each of these strategies, different strategies. And the final thing, what we do after we've trained the model, we try to come up with a model card. Model card is relatively, in scientific world, it's relatively not maybe so new concept already. It was introduced a few years ago. There was this, it was in 2018, 2019, I believe. There was a paper called Model Cards for Model Reporting. You have a link again on this slide. I encourage you to go and read it. And basically the idea of model cards is that you not just show accuracy of your model, but you explain it in a structured way. Like here, for example, this is an example from this article. You write some model details, then you describe some intended use, you describe some factors that can affect the model, you describe some metrics, how you are measuring it, on which data you've evaluated it, on which data you've trained it, what quantitative analysis, what you've done, and also some ethical considerations, caveats, and recommendations. Who needs it? Business needs it, because you've trained the model and someone in the business will make decision how to use this model, and they will use it maybe when you're not around already. And this model card should give them end-to-end view of the model, what you've trained. And also to other data scientists, they go, they read, and they can understand, can they use this model for their scenario or not? Those of you who've trained models perhaps know that there are a lot of some caveats, recommendations, what you have in your mind, and maybe you're putting them in a README file. But this model cards just help to describe it in a more structured way. And here with the face detection screenshot, this is actually from Google Face Detection API service. Describing the API is similar way. So basically this format goes into the industry, and I encourage you to start doing something similar in your projects. At least we try to do it, sorry. Now, let's go into the third phase, which is passing our models from research to engineering. What are our goals here? First, we want to make our research reproducible. over time, if we decided to come back to it in a few years, or by other team members, so they can pick and continue working on it. Then we want to achieve that when we're transferring this models in production, we do minimum or no rework. And also, if machine learning engineers need to improve something, for example, for performance reasons, they do it in the same code what data scientists were writing. So we're getting these changes back, and we can actually use them in future experiments in data science as well. And finally, we want to implement and deliver new changes, some improvements to the model easy, just because we know there will be improvements, there will be some new changes. How we do it practically? First, we rely a lot on Cadre pipelines. There is a link. I encourage you to go and read about it. It's from Quantum Black, and they are like a spin-off from McKinsey, if I remember correctly. So pretty like serious people behind it. And what Cadre pipelines are, here is a visualization of it. Basically, you have these blocks of your code, like nodes where you're writing your code. And these nodes, they are processing some data sets as inputs, and they're producing some data sets as outputs, these red blocks. This orange block is just some parameters that you can feed in. And what is beautiful about it? It helps you to structure your code. When you're writing your code, you can focus on each individual block, this blue block, what you're writing. Then when you're writing your code, you can say, okay, now I want to save all my data sets as CSV files or as, I don't know, pandas pickle files, or whatever you want, whatever format works for you. And then you can debug it easy. So you do go step by step, you debug it. And then when you go to production, you say, okay, great, now all my data sets, these intermediary data sets, will be in memory assign mode. So it's just as if all this pipeline would be one Python function with code in it. It just works. So it's more complex than that, but we actually are putting it directly into production and it works there. So we are pretty happy about it. We migrated to it, I think, over a year ago already, and we are happy since then. So yeah, I encourage you to give it a try. Then what we do, we use pydantic models to validate the data, because one problem what we see with this is that usually if you don't validate your data, then if something changes in this data set, for example, something what you haven't expected in this company's data set, it might cause an error in, for example, this train model node or somewhere there, and it's really hard to debug it. If you add some validations in the, like intermediary validations, then it simplifies your debugging work a lot. We use pydantic models. I know that other teams are using great expectations for it, where you say, like, just on a pandas data frame, like, you expect that the value in this column will not be null or will be within a specific range. We want to try it. We haven't tried it yet, but this is where we're looking at. And also, I know there are teams who try to marry pydantic and great expectations together. This is actually where we're looking at. And one final recommendation, if you develop pipelines like this and you work with some large data sets, as we do, for example, with the medical data sets, they're not large by number of samples, they're large by size of file and processing complexity of the file to extract, for example, imagery data out of this binary format. Then plan your pipelines to work incrementally, because while building these pipelines, you will face many times that you've processed 30% of your data set and then it failed because of some issue. You will adjust your pydantic models, you will adjust your code, you know that already processed samples are not affected. And if you will need to rerun it from scratch every time, you'll just lose a lot of time. So plan how it will work incrementally. We do it by outputting partition data sets in Cadre, and by outputting many of our outputs are pydantic models, so we're just writing them additionally to these partitions. Now let's go into engineering. This is stage 4 out of 5. What are our goals for engineering? This is where we go to the real client who says, okay, I want to use your model in my business system. And this is where clients can say, on which platform they want to do it. We have clients who are saying, I want just a Docker container, I'll put it somewhere on my Kubernetes cluster or Azure container instances. And this is where we usually go for Docker and Fast API. Yes, we use Fast API for implementing web services. We don't use Flask. We've migrated to Fast API some time ago, never looked back, so really great. And yeah, if you are struggling with performance of your prediction web services or something, try Fast API, maybe it will solve it. We have clients who say, okay, we want to go into Azure machine learning. And we have clients who say, we want to go into Azure in Europe and US, but we want to go to Alibaba Cloud in China. And it's the same model. And then how do you deploy it? And this is why it's not that trivial goal. So we want our model to be deployable in all of these platforms. Then we want to ensure common software development practices. So we want to do CI/CD, semantic versioning for our packages, continuous tests for our packages. And finally, at this stage, usually NFRs become very important, non-functional requirements. So you want to optimize your model. And here you may want to implement synchronous versus asynchronous pattern, or you may want to implement some improvements to get very low single prediction time or very high batch throughput. It's where the actual machine learning engineering starts, right? The fun things start. And how we approach it practically. Remember, I was saying that we have this Cadre pipeline, the blue block here. We want to abstract it away from developers. That's why for developers, we are writing so-called proxy classes, which is, you may think of it in programming terms as a public pipeline interface. So basically, it's a class like this one, which has just methods, run pipeline, run pipeline, run pipeline, and then like 1, 2, 3, and then they can have different arguments. And inside it, we actually define what pipeline to run, how to run it, and we know that this public interface will not change. Then we package all of these things, Cadre pipeline proxy classes, in one Python package. We publish it in our private artifacts repository. We use Azure DevOps for it. And then out of that artifacts repository, we can publish it to different locations. Like we can use it in Azure Machine Learning Service scripts, or we can embed it in our Docker container with Fast API, for example. When we do it, one important comment here, if you're picky looking at my slides, yes, we use pip index URL. We don't use extra index URL. The reason for this is pure security. The way how Python resolves dependencies is they will always look into the public repository and the private repository. And if someone in the public repository will publish package with your name but newer version, they may inject it into your code base, and you don't want it. And that's why we use pip index URL. We know all packages will be coming from our private repository. And since we have Python package, we can do what you do with regular Python development projects, CI/CD, continuous nightly tests, checks on commit, some integration tests, and everything. Just in Azure DevOps, we use it as well. Here you may ask, why don't you use Azure Machine Learning Service for this? Because they have like workspace, they also have some pipelines, experiments. Yes, they do. One reason is we want to avoid vendor lock-in, because for example, the pipelines, they can run only in Azure Machine Learning Service. We cannot run them locally. We cannot run them in our Docker container. We cannot run them in Alibaba Cloud. That's why we use the pipelines to orchestrate our Cadre pipelines. This is basically how we use it. And another thing, what we don't like about it, with Azure Machine Learning Service and with other similar services, it's really hard to follow your software development practices, just because your code is there, they're storing snapshots of your code, and it's hard to do versioning, it's hard to do continuous tests, nightly tests, and all this. This is why we tried it, we decided that it doesn't work for us. Now the last stage, production operations. Here, what you want to achieve is you want to meet operations requirements of your client. So usually your large clients will have some requirements around monitoring, alerting, deployment procedures. This is just to make them happy, because otherwise they will not allow you to go into production, right? And then you want to collect new data to improve your model when the model will start working on unseen data. And you want to understand when the model needs to be retrained. These are your goals. How we achieve it? So first, we have practically DevOps engineers, machine learning engineers working together to meet operations requirements. And here, it's really important because basically, this is your machine learning code. Even now, let me make it even more dramatic for you, right? Okay, this is your machine learning code, right? I'll zoom in a little bit. This is your machine learning code. Everything around it is what this team needs to build. DevOps engineers, machine learning engineers, to make it work. Then what we want to do, we want to implement feedback loop from version 1 and data drift monitoring from version 1. Here we use Azure Machine Learning, data drift monitor, or some custom models. For these two, I have a separate slide to describe how it works. Basically, example with document classification. You've trained your model, you have some historical documents, you've applied some labels on them, you've trained your model, you deployed it to the business system. Now, prediction phase starts, new document comes in, your model generates prediction, then there are some users who are looking at this document and they are making decision what to do with it. And this is where you want to collect feedback. For example, have you classified it right or wrong? You may do it explicitly, like give a button to the user like how well we've done it, or do it implicitly. For example, if the user was fixing some metadata in the document and this may mean for you that you've misclassified it, you start collecting it. And this is what the feedback loop is. And you need just to think of it, what you will be collecting. And if there is nothing to collect, how you can engineer it into the solution so there is something to collect. And sometimes it requires you to come up with some clever ways to do it. And basically your feedback loop will be these signals from the system, what labels were wrong. And also these new documents will go into your new training set on which you will be able to train this model to make it better. How do you know when you need to retrain it? This is where you have a data drift monitor. You're constantly monitoring how the documents coming into the model in real production environment are different from the documents you had historically. And if you see that they are very different, like for example, historically you had only 10% of documents of specific type, but in production you are getting 90% of documents of this type, then most probably your model needs to be retrained. Just start collecting data, retrain, deploy a new version. Now, when I've completed with all of this, maybe you were looking at it and you were remembering maybe some of these cool projects where you were participating and you were saying like, yeah, but maybe you're doing this just because your projects are not cool enough, right? So maybe you just try to overcomplicate things because your projects are boring and you try to find how to entertain yourself, right? And that's why I was wanting to show you some cool projects, what we've done and where we've used parts of this or all of this. They are not in engineering in production yet, but we know that we've went through this research to engineering state already. So going into the actual engineering and production operations stage for us will be pretty simple there. This first one, we were detecting diagnosis of a patient based on OCT imaging data. So you see these blocks 1 to 3. We are receiving a cube. This is basically the OCT scan. We are deciding what slices from the scan we want to select. Then we are pre-processing this image. We are selecting specific area. We are augmenting it to increase the size of our data set. Obviously, we do it in the training data only. And then we go into prediction where we have a quite deep model which analyzes each of these slices separately. Then it produces a feature extractor vector. You can think of it as just as this is a barcode where red means very prominent feature, let's say very high value of this feature, and blue means very low value of this feature. And then we have some max pooling, which is extracting out of these vectors for every image global, let's say, maximum vector, where like maximum values of all of these features. And then we do classification from like sigmoid 0 to 1, where 0 means client is healthy, patient is healthy, and 1 means patient is not healthy, right? So it's pretty interesting model, deep model, built from scratch, interesting project, Kedra pipeline, and everything else what I've described to you. Another interesting project was this, where we did also medical data, spontaneous venous pulsations based on RVA videos. On the left side, you see original video, what we're getting from the device. And your task as a task for a medical doctor is to see if you see venous pulsations there. And you can imagine that it's rather hard to see. After we apply our algorithm, now start a video on the right, this is what you see. So AI algorithm, we are pre-processing this image a lot. We're cleaning it out. We're applying a lot of things there. Underneath, there is a link to actual like longer version of medical conference presentation about this thing, where you can see how we've done it, maybe a bit more details. But basically the difference is that on the left side, only well-trained medical professional can see these pulsations. On the right-hand side, already not well-trained, even not medical professional as myself, can see it, right? And this can make a difference because ambulance is coming on site, they're taking a video like you see on the left, feeding it into the algorithm, and the algorithm can produce an image like this. And this can mean that patient has high blood pressure in their head. And this is actually very important information for medics, and they can get it on site with quite a simple device. So quite an interesting stuff. Now with this, I'm gonna close. And what are the key takeaways? If you want to become a better machine learning engineer, or you are a data scientist and you want to keep doing data science and you want to become better data scientist. So first, remember that machine learning is not about training models. Training models, it's really a small part. Remember this image? Here is your machine learning code. I will not try to zoom it in because it's lagging quite a lot somehow during this screen sharing. Yeah, so data scientists, for them, training models, it's really a small part of the work that they do. For machine learning engineers, it's really a small part of their work to deploy these models. There is a lot of interesting stuff to do around. If you consider seriously your career in machine learning, I would suggest that you start focusing. So please think, where do you want to focus? Do you want to focus on research? And then remember, your task is to understand business and to understand data. It's not about massaging the data. Or you want to focus on engineering. And then your goal is how to build this machine learning system so it works in production. And you can decide one or other. I believe all of you will benefit if you look through this Stanford course, which is called Machine Learning Systems Design. If you are seriously considering your future as machine learning engineer, it's a must-view course for you. Really good stuff. They will have new rotations soon, but slides for last rotation or materials for last rotation are available, so you can go find them and just go through them on your own pace. And finally, understand this full cycle of machine learning project. Here is my simplified version. I would encourage you also to dig maybe deeper into that formal ML ops concepts and what stages do they have there. But even in this simple version, research to engineering, engineering, production operations, and project organization management on top. You can see that data science decreases as you go through them. Machine learning engineering stuff increases. But again, this doesn't mean that machine learning engineers who do not know math and do not know how to analyze data, for example, don't do anything in research. For example, in our medical projects, extracting data from these proprietary binary formats, what medical devices produce, this is a very interesting and challenging task for machine learning engineers. And yeah, I would encourage that you just think about the goals of each of these phases. Think how this aligns with how you see it, how you do it. Maybe your goals are slightly different because of some specifics. And I've shared some information about the tools, approaches, what we use. Again, it's just something that works for us. I'm not saying that this is the right way to do it. It just works for us. Maybe in a year from now, I'll say, guys, I was wrong. We found a better way. It is evolving all the time. So think about tools, approaches that work for you. And I do believe that if you do machine learning already now, if you will change your approach a little bit and you will think about this machine learning project approach, what I've shared today, this will help you to become more professional in this field. And out of that, all of us will benefit, because I hope that one day, somewhere in some scientific conference or machine learning conference, someone will say like, oh, I'm working with a company from Latvia. And in Latvia, they're not just training models, they do proper machine learning projects. And this is what we like. This is why we want to work with them. This is why we like machine learning professionals from Latvia. With this, I'm going to close. Thank you very much for your attention. As usual on my slides, here is a link and barcode where you can download this slide deck with all the links. And I can open it for questions, whichever way it works online.